Hello, my name is Mark Norris. I'm an astrophysicist, and in this video I'm going to talk about the things that we've learned about the interstellar interloper 3I Atlas in the first 100 or so days since it was discovered. Now, there'll be no sensationalism here. This is all going to be telling the facts about what we have measured and what this implies about this really fascinating object. As the name suggests, interstellar interlopers, also known as interstellar objects (ISOs), are bodies from other star systems which have been discovered passing through our solar system. July the 1st saw the discovery of 3I Atlas, the third interstellar interloper to be discovered after 1I Oumuamua, discovered in October 2017, and 2I Borisov, discovered in August 2019. So within the last decade, we've discovered 3 of these interstellar objects. One obvious question that arises then is, why are we only discovering them now and not before? And the simple answer to that is that it's only now, in the last decade or so, that we've had the ability to scan the sky so comprehensively with sufficiently sensitive telescopes to find them reliably. 3I Atlas is called 3I because it's the third interstellar object found, and Atlas because it was detected by the Atlas system. ATLAS stands for the Asteroid Terrestrial Impact Last Alert System. It's a network of modestly sized robotic telescopes which search for objects which could potentially impact the Earth. The goal of the system is to give enough warning of an asteroid or comet on a collision course with the Earth to at least be able to evacuate people from an impact site. So they aim to be able to give at least a week's warning of an incoming object large enough to cause significant damage. To date, Atlas has already found 112 potentially hazardous asteroids. Now, they define a potentially hazardous asteroid as one whose orbit will bring it closer to the Earth than about 20 times the distance to the Moon, and which is bigger than about 140 meters in size. For comparison, the Chelyabinsk asteroid that's in the picture, well, it exploded over the Russian city of Chelyabinsk in 2013. That explosion broke windows over a region 100 kilometers wide, and was estimated to have been caused by an asteroid which was only 18 meters in size. Despite that, the explosion was estimated to have released the equivalent of about half a megaton of TNT. Atlas currently has telescopes in 4 locations, with a 5th under construction. They have one on the summit of Mauna Loa on the Big Island of Hawaii, one on the summit of Haleakala, also in Hawaii on the island of Maui, one in Chile, and one in South Africa. And there's one additional telescope currently being built which is going to be located in the Canary Islands. They have so many telescopes spread across the globe to provide as close to continuous coverage of the full sky as possible. The only real blind spot is towards the sun at any given point. The telescopes and their cameras observe a very wide field of view, almost 7.5 degrees on a side, which is as wide as 15 full moons. And the observing strategy is to take 4 30-second pictures of a given region of the sky over the course of about an hour. That allows the system to image the entire night sky between plus 50 and minus 50 degrees declination every day, with the rest of the night sky being observed over every 2 days. You can actually watch the Atlas telescopes take data in real time. If you go to the Atlas project website, they have links to each of their active telescopes. If the telescope is open and observing, you'll get a view like the one shown here, a dashboard that shows you a lot of details about the observations, the current weather, and the performance of that particular telescope. When looking at this image, the circle on the left is the night sky visible from this particular telescope on Haleakala at that point. The squares represent regions that have already been imaged that night. As each of the 4 exposures are made, That particular square gets brighter and brighter, so it's clear how many of exposures have been made there. And of course, once it's done all four, the telescope will move off and image a different region of the sky. Three-eye Atlas was first detected on the 1st of July as an initially 17th magnitude object, and that's actually reasonably bright. You can see in the GIF on the left that Three-eye Atlas is the little dot indicated, and it's clearly moving over the course of the hour and 5 minutes that the images span. This animation shows how essentially all bodies in the solar system are detected by taking a series of pictures over time and looking for objects that move against the apparently fixed background stars. Anything which is in orbit around the Sun or which is moving through the solar system will have an apparently quite large relative motion to the background stars, and so will eventually be picked up. Now, Atlas uses a sophisticated computer system to identify the moving objects. It measures the positions of all objects in the four images, finds any that are moving, then compares their positions to known solar system objects. If no match is found, the software will attempt to fit a first guess orbit for the body. And that is quite important because it allows other telescopes to predict where the object should be so that they can then follow up the observations and help refine the orbit in the subsequent nights. The image on the right shows where on the sky Three-eye Atlas was initially discovered, and as you can see, it's actually quite a dense region of the Milky Way. In fact, when we look at it in detail, when Three-eye Atlas was found, it was basically projected in front of the galactic center. It was right between the constellations of Sagittarius, which is where the galactic center is located, and Ophiuchus. And this meant that the stellar density was extremely high, which subsequently meant that other surveys that could, or in fact should have detected Three-eye Atlas, were unable to find it because it was lost in the noise of those millions of stars behind it. The very rapid motion that this object displayed on the first night immediately piqued people's interest. This was further raised by the preliminary orbit from Atlas, which indicated a possible near-Earth interaction. This caused a lot of interest for people at other telescopes to follow up the object on the next night to refine the orbit and to determine what this thing actually was. With the initial orbit from the first night's data, it was possible to roughly predict where the object would be subsequently, and therefore a series of additional observations were taken on the 2nd of July at a range of telescopes. On top of that, knowing where the object was, and with a rough orbit, it was possible to work backwards and go back into the archives to find images of the object taken previously, but missed. They're so-called pre-covery images. Images of Three-eye Atlas have now been found as far back as the 28th of March. The combination of newer observations and older ones has allowed the orbit of Three-eye Atlas to be refined, and one effect of that was that the apparent close approach to the Earth rapidly went away. It was just spurious based on a poor initial orbit. But a surprising result was that the path of the object had an extreme eccentricity of over 6. This alone indicated that the Three-eye Atlas must be interstellar in origin. Eccentricity is one of the parameters that defines an orbit or path through a star system. The simplest orbit would be a circular orbit, where the heavier body, the Sun, say, is at the center and the planet goes around it in a circle. This would have an eccentricity of 0 by definition. The Earth's orbit has an eccentricity of 0.017, so very close to circular. Now, as the eccentricity increases, the orbit becomes increasingly elliptical. And once the eccentricity exceeds 1, the smaller body is no longer gravitationally bound to the larger one, so will leave the system. The plot on the right indicates several orbits, including a circular orbit, an elliptical one, and the paths of objects with the same eccentricities as the 3 known interstellar interlopers. So Oumuamua, when it was discovered, was found to have an eccentricity of 1.2, and at that time that was a record. Only man-made objects like the Voyager probes had higher eccentricities. Borisov was then found to have an even higher eccentricity of 3.36, and Atlas, with its eccentricity of 6.14, blows that out of the water. So that is by far the record holder for objects with eccentricities measured. Now, one of the reasons why the eccentricity is so high is because Atlas is moving so incredibly fast. At discovery, it was already moving at 61 kilometers per second, which is roughly twice as fast as the previous interstellar interlopers, and also twice as fast as the orbital velocity of the Earth around the Sun. So this object cannot be bound. It's just flying through the solar system on its way back out into deep space. The speed of Atlas was increasing at discovery as the gravity of the Sun pulls it towards it. It will continue to increase its velocity until it makes its closest approach to the Sun, which will still be outside the Earth's orbit, after which point it will begin to slow down again as the gravity of the Sun pulls it back. But even when it has fully left our solar system, it will still be moving at around 58 kilometers per second, which again is much, much higher than the other interstellar interlopers when they will leave the solar system. Now, the direction that 3i Atlas is coming from is interesting. I've made up a quick plot here showing the paths of the three interstellar interlopers relative to our solar system. The orbits of the outer planets are also shown here to help indicate the location of the ecliptic. This is the plane which all of the planets of the solar system orbit the Sun around in. In this plot, you can see that Atlas actually came in quite close to the plane of the ecliptic at 175 degrees, which means it is retrograde. It's moving in the opposite direction to the planets and inclined only 5 degrees to the plane of the ecliptic. Both previous interlopers arrived from much higher angles to the ecliptic, and therefore they appear to essentially be plunging down on the solar system from above. Now, some of the more excitable types out there have used the fact that Atlas is arriving close to the plane to argue that this must mean it's being directed or piloted, and this is obviously highly unpersuasive. We only have 3 of these objects. We don't have enough statistics to know whether or not we expect them to arrive from random directions, or to have some preferred direction they will come from. One obvious example might be that they might arrive with preference to come from the plane of the disk of the Milky Way, because that's where most of the stars are. Now, if they do arrive from random directions, then they're just as likely to arrive close to the plane of the solar system as far from it. So I don't think you can infer anything substantial from the fact that this one object has come in quite close to the plane of the ecliptic. This image shows the current situation as of the 22nd of October 2025, and as you can see, the Earth, the Sun, and 3i Atlas are all aligned. So this means that 3i Atlas is hidden behind the Sun currently. It will be about a month before it moves away sufficiently along its orbit and the Earth moves around the Sun on its orbit that it becomes directly visible from the Earth again. Now this image shows the situation as of November the 30th, by which time 3i Atlas will have moved beyond the Sun, and additionally the motion of the Earth in its orbit will bring it further around the Sun to give a clearer view of 3i Atlas. So in practical terms, from mid-November onwards, we will begin to be able to see 3i Atlas initially very close to dawn, just before the Sun rises. And as time goes on, it will rise earlier and earlier in the night. When 3i Atlas does reappear, it will be the first time that it becomes observable to astronomers at higher latitudes in the Northern Hemisphere. This image from the Free Stellarium software shows where 3i Atlas will appear to be for an observer in the UK at around 6 AM on the morning of the 30th of November. At this point, it will be seen in the constellation of Virgo, and it will be high enough in the sky to be observed with a typical amateur telescope equipped with a digital detector. We will certainly attempt to observe it ourselves because we are very lucky at the University of Lancashire to have a very powerful modern 70 centimetre robotic telescope located at a reasonably dark site. With good dark skies, we would hopefully be able to observe 3i Atlas until the February-March sort of time frame, at least based on predictions in the plot on the left for how it will fade as it gets further from the sun. In the meantime, we have no direct line of sight on 3i Atlas from the Earth. Now, that doesn't mean that it is completely unobserved. We are currently relying on observations from probes on or in orbit around Mars. The animation shows an observation from the ExoMars mission, which detected 3i Atlas as it passed by Mars. We shouldn't expect too much data from these missions, however. They simply weren't designed to look at faint objects in space. They were designed to take pictures of the brightly illuminated surface of Mars. This means that their cameras often have hard limits on how long they can expose for, sometimes as short as half a second, which makes 3i Atlas simply too faint to be picked up by their detectors. As we'll see later, however, there is one interplanetary mission that should provide some useful data during the period when 3i Atlas can't be seen directly from the Earth. So what have we learned about 3i Atlas so far? Well, if you go to the Astrophysical Data System, you can search for scholarly papers which mention 3i Atlas. And if you do that, you will find that there are already over 50 papers or astronomers' telegrams reporting results on 3i Atlas. We do have to be a little bit cautious, as given that we've only known about 3i Atlas for a little over 100 days, most of these papers have not yet completed peer review, so they may change a little during the reviewing process. The first few have begun to be accepted by journals, but most are still in the preprint stage. One of the things we learned as early as the second night was that 3i Atlas is definitively a comet. It is not an inert body like an asteroid, it is actively releasing gas and dust from its surface. On that second night, the 2nd of July, cometary activity was detected by several independent groups. The way it was detected was the way that cometary activity is usually detected. By examining the size of the object, it was noted that it was not a point source like a distant star. It was what astronomers call resolved. It was measurably extended, which meant it had to be big. And what's more, it was asymmetric. It was longer in one direction than the other. This is classic cometary behavior, where there is a tail that extends far behind the coma, which itself surrounds the nucleus of the comet. As 3i Atlas has approached the Sun, the data has got much better, both because it's closer to the Earth so we can discern more detail, and because it becomes more active as it approaches the Sun and heats up. So now we have these very beautiful videos from the Gemini Observatory which show a very obvious tail which extends far away from the coma and the nucleus of the comet. This is a color version of the same data, and it clearly reveals the cometary nature again. If we look at this picture, there is absolutely nothing unusual about the shape or structure of this object that would set it apart from any ordinary solar system comet. It looks totally normal. We were fortunate that there were serendipitous observations of 3i Atlas by the Transiting Exoplanet Survey satellite. This is a satellite whose main goal is to watch large numbers of Milky Way stars for the telltale drop in brightness caused by a planet in their star system passing in front of them. By pure dumb luck, it happened to be looking at the right patch of sky so that 3i Atlas passed through it. The TESS observations show that it's likely that the cometary activity started when the object was as far as 6 to 9 times the distance from the Earth to the Sun. And that is quite far. such large distances, the illumination from the sun isn't sufficient to warm water ice enough to sublimate directly into gas. Now the plot you can see comes from Putzier et al. 2025, and the blue lines show different models for the surface layers of the comet, and the dashed horizontal lines show the temperatures needed for various volatile materials to sublimate. You can see that water is not expected to escape from the surface of the comet as a gas until it's around 2.5 times the Earth-Sun distance. So out at 6 to 9 AU, we have to be looking at molecules like carbon monoxide, ammonia, or carbon dioxide as the ones responsible for driving cometary activity. Putzier et al. Used the Goodman spectrograph on the SOAR telescope, one I know a great deal about because I helped commission it, to examine the 3I Atlas on the 3rd of July, and they saw no sign of any gas phase material at all when the comet was at 4.4 AU. Now there must be some gas present because something was causing the coma and the tail to form, but whatever it was at a level that wasn't detectable to them at that point. Likewise, on July 4th and 5th, the Very Large Telescope and its instrument X-Shooter was also used to observe the comet, and they've also failed to detect any gas phase material. The spectra on the right show their observations, and they show two wavelength regions where you would hope to pick up emission from OH, so oxygen and hydrogen, and CN, carbon and nitrogen, bonds, and in both cases neither is seen. You can see a few spikes which are in just the right region that you might get excited because you think you've picked up OH and it's the presence of water. But sadly, however, these spikes are just due to defects on the detector of the instrument, so nothing to get too excited about. Initially, water was only detected as ice. Yang and collaborators used the infrared telescope facility and its SPECS instrument on the 5th and 14th of July, and by fitting the spectrum of 3I Atlas, it was possible to see that evidence of dips caused by water ice absorbing light. The authors found that their best fit model for the composition of the coma, the dusty shell that surrounds the nucleus, was 37% water ice and 63% amorphous carbon, which is essentially soot like dust material to you and me. Not long after that, the Swift satellite and then the James Webb Space Telescope were pointed at 3I Atlas, and they both detected gaseous water. So that is water that must have sublimated, that has gone directly from a solid, from ice, to a gas phase, with no liquid phase in between. And it does this because the vacuum of space doesn't allow liquid water to exist. So it converts directly into a gas and escapes from the nucleus of the comet. And as it does this, it will drag some of the particles of dust that were detected along with it. This gaseous water was detected at slightly larger distances from the Sun than typical, 3 astronomical units compared to a typical 2.5, but that's not particularly unusual. It's not particularly outrageous or notable. JWST did make one particularly interesting discovery, which was that the ratio of carbon dioxide to water was very high, about 18 times higher than is typical for solar system comets. But this is not the most extreme measurement of this ratio we've seen. A solar system comet called C2016R2 was observed to have an even higher carbon dioxide to water ratio. So while high, it isn't like 3I Atlas, it's unlike anything we've ever seen before. And such elevated ratios might actually be telling us something about the chemical composition of the star system it formed in, or alternatively about the location within its star system where it formed. So these kind of differences can be actually very interesting. Additionally, the carbon monoxide to water ratio is much more typical of those measured for solar system comets. So given these ratios, it does seem that in the period while 3I Atlas has been actively observed, it's carbon dioxide that is driving the bulk of the cometary material. The carbon dioxide is heating up in the light of the sun, it's converting to a gas, and as it escapes the surface of the nucleus, it is pushing lumps of ice and amorphous carbon off the nucleus with it, creating the coma and the tail of the comet. There are now longer-term monitoring projects of the comet using the Very Large Telescope and the UVAS and X-Shooter instruments. These two instruments detected atomic nickel coming off the comet around July 20th. You can see this on the plot on the right as the spikes present in the central wider parts of the plot. You can see that the lines appear around the 20th of July and then they increase in size, indicating increasing amounts of nickel being detected as time goes on. Likewise, from August the 15th, CN started to be detected, and it increased in strength as time went on as well. Now again, this is not particularly shocking. Solar system comets do also release the same types of material. Follow-up work with the Keck telescope and the KWCI instrument mapped out in 2 dimensions how the nickel and CN are distributed, finding that the nickel was considerably more centrally concentrated than the CN. The difference in distribution could provide clues to the source of the nickel. It's thought that there are 2 possible sources. The first are metal carbonyls, combinations of, in this case, nickel with carbon monoxide molecules. The second possible source are nickel PAH molecules. PAHs are polycyclic aromatic hydrocarbons, which are composed of benzene rings of carbon atoms bonded to other atoms and molecules. In either case, once these solid materials are released into the coma of the comet, they will rapidly be broken apart by UV light from the sun, leaving the nickel in its isolated atomic form. It's thought that the distribution of CN and nickel should give a clue to which of the 2 options is driving the nickel release, but this being astronomy, it's almost certain that both scenarios are occurring at the same time. It took until the end of August before iron was detected, but finding iron itself isn't unusual. Nickel and iron are very similar metals inhabiting the same area of the periodic table, and they're formed by essentially the same events, supernova usually. So where you find nickel, you do expect to find iron. Initially, the nickel to iron ratio was unusually high, but this has been trending down towards a more typical ratio for solar system comets over time. So for some reason, nickel was being released more readily early on, and as the amount of iron released has increased, that's sort of normalized this ratio. And that's probably telling you something interesting about the composition of the outer layers of the comet. Despite the fact that we see 3I Atlas releasing quite a lot of gas, it hasn't shown any sign that this gas is providing any measurable thrust to alter its orbit. There is no sign of non-gravitational acceleration. It is moving exactly as we would expect given its incoming trajectory, its velocity, and the gravity of the Sun. This should be indicating something interesting. Oumuamua displayed non-gravitational acceleration despite having no detectable outgassing. It must have been there, we just couldn't pick it up, it was so small. Borisov also showed non-gravitational acceleration, but this was seen to outgas, so it makes sense. The fact that we see 3I Atlas is not displaying a non-gravitational acceleration is probably because it is considerably more massive than the other 2 interlopers, and therefore it's much harder to change its motion, and there simply just hasn't been enough gas released to push it out of its original orbit. Using HST, Jewett and collaborators were able to estimate that the nucleus of 3I Atlas was likely to be smaller than about 2.8 kilometers in size, but they weren't able to place any strong constraints because the coma dominates the light output coming from the comet, and it is essentially hiding the nucleus, which is sort of wrapped within this coma. And that size, 2.8 kilometers, compares to about 100 meters in size for Oumuamua and 400 meters for Borisov. The lack of detectable non-gravitational acceleration also provides another estimate of the mass and hence the size of the nucleus, which comes out at around 5 kilometers. Either way, 2.8 or 5 kilometers in size would indicate that 3I Atlas is much larger and therefore significantly more massive than the previous two interlopers. Spectroscopy of the comet shows that 3I Atlas is very red, though it is comparable in color to Oumuamua and Borisov, as well as to the D-type asteroids of the solar system, and it's even considerably less red than the very unusual solar system body Pholus. Now, having looked at several of these spectra myself, I can see some signs that the color is becoming less red over time. And this would make sense because as the object approaches the sun, more and more ice and water is released, and these materials are considerably more reflective than the amorphous carbon dust which had dominated the coma at greater distances. And so, because of that, the additional reflectivity of the ice and water will mean that you are reflecting more of the blue light, which the dust would have preferentially absorbed, and that sort of shifts the shape of the spectrum over time, making it appear less red. So where did this thing come from? Well, there have been two studies already which use data from the Gaia survey to search for possible past interactions between 3I Atlas and other star systems. Gaia is a survey of 2 billion stars in our galaxy, where we're measuring the distance as well as how those stars are moving through the galaxy. By taking the Gaia catalogue and the known path that 3I Atlas has taken to come to our solar system, it's possible to wind back the clock and determine if the comet and any known stars were ever close to each other. Neither of the two studies found any close interactions, certainly in the past 10 million years. The closest approach they found was something like 0.2 parsecs, which is a considerable distance. It's a 20% of the distance to the nearest star, for example. And that would not be close enough to alter 3I Atlas's trajectory in any meaningful way. Interestingly, though, both studies did conclude that 3I Atlas originated from the thin disk of the Milky Way, which is a population that the Sun is a member of. Both plots on this page show the locations of known thin disk stars in these various parameters, and we see that 3I Atlas appears consistent with those populations in both of these plots. Other papers use different approaches. Hopkins et al. Used a model for how the population of interstellar bodies should behave to infer that 3I Atlas is likely to be considerably older than the previous interlopers. They also concluded that it shares its orbit with slightly older lower metallicity stars that could be from the thin or thick disks of the Milky Way. Now initially they claimed it was from the thick disk, but after feedback they modified to say it could come from either. Kakarov and Loeb and Taylor and Seligman essentially agreed that 3I Atlas is older than Oumuamua and Borisov, and also thought that it could have come from the thick disk. So at the moment, people agree that 3I Atlas is probably older than Oumuamua and Borisov, but they disagree about whether or not it came from the thin or thick disk of the Milky Way. Now, if you're wondering why it says Kakarov and Loeb 2024-2025, it's because they edited a paper submitted in 2024. It isn't because they were writing papers on 3I Atlas before it was discovered. Believe me, it confused me no end when I found that paper. So thin disk, thick disk, why do we care? Well, most disk galaxies are found to have two disk-like structures, which generally combined contain most of the stars for a disk galaxy. In the Milky Way, the thin disk has a scale height of around 300 parsecs, So that is, the density of stars will have dropped off by an exponential amount 300 parsecs above the midplane of the disk. The thin disk is where star formation is currently ongoing, and as such it contains stars of all ages, from 10 billion years old to just being born now. The stars in the thin disk are almost completely rotationally supported. That is, they go around the center of the galaxy in nice orbits which don't deviate much in height above and below the plane. The thick disk, as the name suggests, is thicker, with scale heights of about a kiloparsec, which means that the higher above the plane of the disk you go, the more dominated by thick disk stars you will find it. The stars with a thick disk generally have older ages and tend to be dynamically hotter. So most of the support that stops them falling to the center of the galaxy still comes from their rotation about the galactic center, but some comes from what we call velocity dispersion, essentially random motions that will bring them further up and out of the plane of the disk. So why we care is that, of course, to date, we have only ever directly sampled bodies from one star system, our own. If interstellar interlopers come from thick disk stars, we might be able to directly sample star systems that formed billions of years before our own, and hence these would be chemically completely distinct from our own. These stars and their planets and comets would have formed at a time before much of the chemical enrichment caused by supernova or merging neutron stars or just general stellar evolution that was necessary to give the elements that we find in our solar system. So it will give us a really great comparison to our own star system and let us track the evolution of the building of star systems over time. One of the first questions everyone asks when we discover one of these things is, can we intercept them with a space mission? Either just to get a closer look, or ideally to sample it and bring some material back to Earth for analysis. And in this case the answer is sadly no. 3I Atlas is just moving too fast. From Earth you'd need to give a spacecraft, which you haven't built yet of course, 24 kilometers per second of extra velocity to be able to reach the comet. But most spacecraft we build have a delta V of a few kilometers per second, because it's really expensive to lift fuel into orbit, and if you put extra fuel on a spacecraft, you have to also put even more fuel onto it to account for the extra weight of the fuel you are carrying. So the spacecraft just gets bigger and bigger and bigger and extremely expensive. So spacecraft are built to use the absolute bare minimum of fuel to achieve their goals. Now, even if there was a way to send a spacecraft from Mars, which 3I Atlas passes much closer to, it would still require 5 kilometers per second of delta V, which is far beyond what any probe currently around Mars has left. Now, in the future, this might not be totally hopeless. There is a mission already under construction called Comet Interceptor to be launched in 2029. And this will launch a spacecraft into deep space parking orbit, where it will wait for a suitable solar system or interloper comet to intercept. So at the time of launch, it doesn't know what it will be intercepting, but if the right interstellar object comes along, it could be sent to intercept that. However, even if that mission was up there now and waiting, it still wouldn't be able to intercept 3I Atlas, because 3I Atlas is just moving too fast. So an interception might happen in the future, but it isn't going to happen for this object. So what's next? Well, as I said before, 3I Atlas is currently moving behind the Sun, so we can't observe it directly from Earth. Fortunately, however, the Jupiter Icy Moons Explorer, JUICE, will be passing relatively near to 3I Atlas on its way to Jupiter during the period when we can't observe it directly from Earth. So there are plans to have JUICE start observing 3I Atlas on the 2nd of November, just after 3I Atlas makes its closest approach to the Sun, which is when it should be at its most active. JUICE will then continue observing until the point where observations from Earth can begin again. The three interstellar objects we've detected so far should just be the tip of the iceberg. The Vera Rubin Observatory is just starting the Legacy Survey of Space and Time, the LSST, and they have already proven that they can detect these objects, because it turns out they observed 3I Atlas. And in fact, they would have discovered it potentially months before Atlas if it wasn't for the fact that the observations that they found it in were taken while they were still setting up the telescope and no one was really looking for these kind of objects. Now, the LSST is estimated to detect between 0 and 70 Oumuamua type objects per year, or 6 to 51 over the 10-year survey, depending on whose estimates you take. These two numbers, or two ranges of numbers, are both very uncertain, though they formally agree, and they're uncertain simply because we don't know how many of these things are out there yet. But there is a realistic shot that we will detect tens of these things a year, and that's just the asteroid types. The comet types might actually be more common, given that we've found 3 interlopers so far, and 2 of them have been comets. So on to conclusions. Well, the first one is that 3I Atlas is undoubtedly a comet, despite what some more enthusiastic people might claim. Yes, it has some unusual properties relative to solar system comets, but these are essentially within the bounds of what we've seen in the solar system. And the differences make even more sense when we consider that this is an object from a different star system. It likely formed with a different mixture of chemical elements and in a completely different location to the types of comets that we see coming from our own star system. We just expect it to be different. We'll learn a lot more about this thing when it reappears in November, just after peak activity. And we should also bear in mind that all 3 of the interlopers that we've seen so far have been very different. With the LSST starting operations, these objects are likely to be just the tip of the iceberg. We're hopefully going to be able to get samples of these things in future, and that will allow us to work out actually just how typical the comets of our solar system are, or whether in fact they're unusual compared to the populations out there in the Milky Way. Comet Interceptor will be well placed to intercept a future interstellar interloper if it appears with the correct trajectory in the early 2030s. So we may get an embarrassment of riches in the early 2030s where we have samples of these things that we've detected and one that we've managed to get up close and personal with. So I hope you enjoyed this video. Please feel free to give your feedback in the comments and let me know if there's something about this topic or any other area of astrophysics that I might be able to cover.